Hello and welcome to complex ions or complexions, also known as coordination compounds. So it is truly two words, and they are ions that are much more complex than just say sodium chloride, which is a sodium and a chloride. The old way we used to write them back in 221 was we would say this is iron 2 chloride hexahydrate. So we talked about them as hydrates, and this is wrong. It turns out that the water is connected, attracted to the iron. So the ion is always going to be one of the transition metals. And this is what makes the transition metals so cool. And it has to do with those d orbitals. So we're going to be doing a review of electrons and quantum. And that's why I was able to make the quantum leap back into my mermaid outfit, back into the ocean. All right, so oxygen or water, remember water is covalently bound or covalently bonded, and the oxygens are pulling the electrons more. So we get a dipole, we get a pull of electrons. This negativity of the oxygen is attracted to the positivity of our transition metal. And so we get 6 water molecules around it. So we would say this has a coordination number of 6 because there are 6 waters around it. That is one of the questions on your final. It's one of those questions that should only take you 20 seconds. You look at it, probably only 10 seconds. You go, oh, I know that one. The chlorides are actually on the outside. Because of this +2, this has a +2, we need 2 chlorides. So they're just out here attracted to the complex. Just like cation, right, is our complex, and the anion is the chlorides. Now the complex can be a cation, it's always going to be made up of a transition metal, but it depends on what's around it. And these are called ligands or ligands. I've heard it said both ways, which means one way of thinking of it is like teeth or binding. They often talk about hormones and neurotransmitters and this plethora of neuropeptides. They find a new one every day as ligands, and they bind the receptor. So these are called ligands, and they bind. The ligands are either going to be neutral. They're either going to be polar neutral. They have to have a negative area, because they're going to always be attracted to the positive. And so the ligand could be neutral, and that would be something like H2O or NH3. So the nitrogen in this case would be the negative area, or it could be a true anion. So something like chloride. In this example, the chloride is not, but chloride could, or hydroxide, or anything like that. Now, the thing that these ligands have in common is they are monodenate. And my shadow gets in the way because of where the window is. But these are monodenate, meaning they only have one tooth. So denate means a tooth. So the oxygen is the only thing that's attracting. And we're going to do practice, so you'll get the hang of these. Polydenate would mean that they have multiple teeth, and there are actually many of these, and there are new ones always being made. So we're only going to see 1, 2, or 3 of these. The most common one, and the one I can draw, is oxalate. So oxalate was a polyatomic that way back in 221 you should have learned. So C2O4, and it has a -2 overall. So the whole thing's a polyatomic. And what it looks like, more so you understand, you are going to get to draw one of these out in a couple pages, because we're going to do a review of Lewis structures a little bit today too, is the 2 carbons are hooked to each other, and carbons always make 4 bonds. And so one of the oxygens is double bonded to each carbon, and one of the oxygens on each carbon has a single bond. Now oxygens like to make 2 bonds, and the way I know that, besides being the all-knowing mermaid princess, oxygen is in family 6A, has 6 valence electrons, so it needed 2 more. So if we did a full Lewis structure, right, the ones that have a double bond, those oxygens are complete. These oxygens, because they have only a single bond, they each have a negative on them. And those negatives are the polydenates. So if we were showing these, let me erase the word oxalate. Let's say this was connected or attracted to our iron, we would show, so again, covalent bond, we show a line, and then attraction, right? These are a type of IMF, which is in some cases ionic attraction or an ion dipole attraction in our water example up there. So we just have this attraction. This right now is a coordination number of 2, even though there's only 1 ligand. So an oxalate always doubles however many oxalates you have there. What are some other ones? All right, there is another polydenate, we're going to call it abbreviated as EN when we're writing out the name, but it stands for ethylene diamine. And I don't know why they write 2 M's there, because amines always have just 1 M. But an amine is a nitrogen. And so there's 2 nitrogens hooked together. Oops, I'm so sorry. The ethylene means 2 carbons. And then the diamine means there's 2 nitrogens. So each carbon then has a nitrogen on it. And it is those nitrogens that have the attraction. And then the carbon, I'm pretty sure, has a double bond or a single bond between it, or a triple bond. That part doesn't matter. It's going to be the nitrogens that have the attraction because they have the negative area. So it is also a polydenate. It can always have, for every ethylene diamine word we see, there's 2. All right. Yeah. There's many others. Actually, one back to Jessica talked about in her talk, Fritz Haber, who unfortunately chlorine was dropped during World War I when they used chemical warfare. And the treatment they found for it was a ligand that had a coordination number of that one ligand could bind 6 things. It had 6 teeth. And that is a picture that is shown over underneath the copper one. So that is EDTA, which is, did I write down what EDTA stands for? Ethylene diamine tetraacetate. So it has 6 teeth. And so it's really good at pulling things out. And so they used it. It is still used in almost every other country except ours, because we still are for-profit medicine. But in countries that are not for profit, they use it because the largest cause of heart disease is eating animal products and getting all this calcium into your arteries that make your arteries not work so well. And so we have to pull that calcium out. Now, it sounds really funny, right? But I talked about in the acidosis that the calcium comes out because we're eating diets that are very acidifying, also a high sugar diet. And so all this calcium ends up depositing in your arteries, and your arteries can't function. And so in other countries, like in this country, we just cut the heart open. I have a dear friend who, he's only 70, and he had a massive heart attack last Monday. Had complete blockage of one of his arteries. So they had to go in, they put 2 stents in, and then they sat him down. And this is the beautiful part. They sat him down and said, if you don't change, because they've done this enough to know the stints don't work if you don't change. If you don't change your diet. And this guy admitted he ate crap, and he said, I am changing. He's scared. And he ate McDonald's. He went to McDonald's. And I was having this conversation with Joey today. I think the reason this guy made it to 70 is because he didn't eat crap until he was probably 50, because we didn't have this crap when I was a kid. All right. And yeah, you guys need to stop now, because you don't want to be that at 30 or 25. And I've heard these stories. You need to eat real food. If you get nothing else from my class, other than that I'm totally crazy, is eat real food. Doesn't mean you have to prepare hours and hours, which is really wonderful because it's a meditation, right? It means you eat apples and oranges and bananas and berries instead of eating this highly processed food. All right, so back to coordination compounds. Oh, hemoglobin, by the way, the heme inside the hemoglobin has 4 teeth, and that's how it works. Same with in chlorophyll is the same, the polyporphyrin ring, and so it has 4 teeth and it's holding the molecules together. In the center of hemoglobin, that heme is an iron, and in the center, it's the same molecule of chlorophyll. It is magnesium. And so eating your greens, you get lots of magnesium. So when you're getting muscle cramps, eat your greens. All right, let's see. What other words of wisdom do I have on this page that I should share? Yeah, this binding is because there's empty d orbitals in the iron. And so it's able to do this. All right, so the coordination number is the number of teeth. So we're going to go through these examples, and we're also going to do oxidation number, and the oxidation number is what we were calling the charge of the transition metal. It is actually an the oxidation number, which is +2, building in to everything we just did. And that you may have just had an exam on, since you're probably all going to watch this after your exam. All right, the rainbow squid is here to help me. And I have to tell you, I got this outfit, and I didn't know what it was. A former student gave it to me, and it was finally, so I'm going to dare to show it to you, the full tail, because Megan would be intrigued that, so that's why you see me shuffling around. So my mermaid tail is there. Megan, you need one, since you have the mermaid hair now. And I wore this shirt because it reminded me of her mermaid hair. All right, so let's walk through our examples. So zinc. You might be like, I'm good. I got the idea of, this is actually review for the final also, because we're going to bring in a bunch of little pieces here and there. All right, this, we just don't show the cation, but this would be an anion coordination compound. Zinc, remember, likes to be a +2, so its oxidation number. There are 4 teeth. These are hydroxides. So our coordination number is 4. Simple enough. We are going to name these. Yeah, we're going to name them. And iron. So I'm going to leave a space there for naming. Let's go through the coordination number thing first. This is the one we just did. They show the complex ion is in a bracket. They are truly called coordination compounds because it can end up neutral. This one I actually showed the anions to balance out, but this is an ion because it has a net +2, which is the iron, and a coordination number of 6. All right, so this one we showed the sodium in the front, the brackets around the coordination compound. Oh, and there's our friend oxalate. And so for every oxalate, you double your number. So the iron is a +2. No, I am sorry. Each of these oxalates is a -2. Times 3 would give us -6. Oh, I was right. The sodiums are +1 times 2, so I have a +2 there. So my iron's a +4? Because your teacher can't read. I've lost 3 pair of glasses during this class. They're somewhere in my house, and I can't see to find them. And so this was sodium with a 3, and there we go. So that has a +3. This has to have a +3, so we cancel out all the oxalates. So our oxidation number is +3. That's going to be important when we get to the name. And then our coordination number is 6, because every oxalate has 2 teeth. All right, the last one is cobalt. There's our ethylenediamine. And there are 2 chlorines, and then our bracket, and then the other chlorine. Now, the chlorine outside the bracket is important for our charge. So all of these chlorines give us a -3. So that means my cobalt has an oxidation number of +3. So you have to look at all of them, all the chlorines for your oxidation number. But when we do the coordination number, we only look inside the bracket. We only look at the ligands. Ethylenediamine is neutral, no charge. The chlorines give us a -2. I'm sorry. The ethylenediamines each count double for teeth. So 2 times 2, which is 4 teeth. And each chlorine only counts once. So we have a coordination number of 6. 6 is by far possibly the most common coordination number, because they're going to make octahedrals. Remember octahedrals? The 4s are also really common. You can also see 5s and 3s. You really don't see 2s. Those don't do much. And the 3s are kind of small too. You could see that. But 6 and 4s are the most common. And then there's a cartoon at the bottom where somebody's made it with 7 teeth, which is really funky. And those of you who had me for 222, if you remember, you had one where you had to draw something. What would it look like if there were 7 things around it? And they've even gone up to 8. These things are really cool because they do really cool, beautiful colors. All the beautiful stones that you find, it turns out it's because of these complex ions, because this is where the colors that we see coming from. And my understanding of these is very basic, based on what I teach you. If you're really into them, Dr. Russell's doctorate is actually in these, and he has books and books on them. And so you can ask him, and he will give you books, and he will talk to you for hours about it, which is hard to believe because the man doesn't talk that much because he's a man. All right, we're going to name these, and there's a lot of words here at the page, and then it has a place for you on the next page, or maybe on this page. Maybe I'll rearrange this. All right, so naming. This, when we write the complex, we show the zinc first, or the iron, or the cobalt. When you write your name, you always do ligands, and then the metal. I don't know why. That's just how they did it. And so we're going to do it that way. So, OH. Now, there's another piece of information. This is where all these words come from. And this is really kind of funny, and it's always a fun way to end. And it's a bummer I don't get to do these live because we always get to be really goofy with these. But they don't end with ides because they're not ions. They are ions, but they're attracted by these teeth, and they're like there now with the zinc. They're not meandering around. They're meandering in this big complex. And so instead of calling it hydroxide or a chloride, when they are a ligand, the ending of IDE changes to an O. Like, oh. So, hydroxide, we call it, we say there's 4. So you guys remember 4 is tetrahydroxo. Really easy. There are a couple of naming questions on the final. So this is also a good review of some of the naming stuff. So we say tetrahydroxo, and then we say zinc. And then we put a charge for the zinc. And there was an extra piece that your teacher often forgets. This piece isn't on the final. And since you don't have a in-class quiz, it doesn't matter that much. Zinc, we put the Roman numeral 2 to say it has an oxidation state of 2. All right, this one is shown as an ion. We didn't cancel out the charge. So you would end with the word ion. And the little piece of information I forgot, because negative coordination compounds are not as common as the positive ones. I know on here I showed 2 that come out negative, but when it is negative, you put the word 8. It's like it ate something up. So it's tetrahydroxo zinc 8 2 ion. Really interesting. All right, let's do the iron one. So our first piece is going to be about the water. So we would say hexa aqua. So H2O, Nothing gets its name with this. My theory is this was the end of a really long, like, week of the International Union of the Pathetic and Apathetic Chemists, and they were just like, okay, let's just make up names. So water is now called aqua. They wanted equal opportunity. I don't care if you show 2 A's, but they do drop one of the A's. So it's hexa aqua, and then iron. And iron had a +2 oxidation state. So it's hexa aqua iron 2. I don't put the 8 there because my complex ended up positive overall. So the 8 is only if the complex has a negative charge. So it's the anion. Here my complex is the cation. So hexaoxa iron 2. Now, in all honesty, it would be called ferrous. I'm okay with iron, but they do go back to the Latin names of the ones that have Latin names, like iron and copper, and even gold. I don't know if we get a gold one. And then we name the chlorines. Now the chlorines are truly outside, so it comes after the 2. And this is called a chloride. This part is the cation, my complex. So it's a complex cation. Cats are pretty complex. My Rocky is. And then the chlorides are the anions. They are just attracted to it. All right. Let's do the next one. Maybe I should do this piece outside. Now, on this one, the sodium was shown first because it's the cation. We always show the cats first. Cats come first. So you're going to say sodium first. And then we're going to do the complex. And in the complex, we name the ligands first. An oxalate is no longer called oxalate. Oops, I'm sorry. I'll tell you that there's 3 of them. But oxalate is going to be called oxalate-O. The O is because it has a negative charge. You have to tell me there are 3 of them. But, of course there's a but, because it's complex ions. We have to make it as complex as possible. The but is, instead of saying tri, because it's a polydenate, you say tris. That's why for those of you who just copy my answer key and don't even listen to this, you're not even going to wonder this because you're people who copy. But hopefully, if you're watching this, you're not just going to copy the answer key. You might look at it and appreciate it, and maybe you'll copy it. But it is tris because it is a polydenate. It's a polydenate ligand. So it would be bis if there were 2. If there were 3, it is actually tetrakis. So it would be 4 kisses, but they're all double kisses. So it's called a tetrakis. All right, you can ponder that. And now we have to say the iron, and the iron has a 3. So you can say iron 3. I am perfectly fine with that. It is actually called ferric. You can say ferrous. This gets to back in the good old days when I went to school and we had to memorize everybody's name and every Latin charge. When iron has a 2 charge, it's called ferrous. When it has a 3, it is ferric. We don't write the word ion because these came out neutral overall. Cation first. My complex. Oh, somebody wants to say, sorry. Because this was negative, see, it would be iron 8 or fer 8. So it didn't matter what I had to memorize when I was a young wee little mer kid. So you can either say sodium tris oxalato ferrate 3 or ironate 3. 8 3 of what? I don't know. All right, let's do last one. Cation first. In our cation, we now have 2 different ligands. So there are rules. Ligands go alphabetically. When you write the complex, I don't know what the rules are. You show the metal first, then you show the ligands, and then you put it in brackets. But when we write the name, They made rules. Chlorine comes before ethylene because C comes before E. Should we do the alphabet again? A, B, C, D, E. C came before E. All right. C. Dichloro. So there's two chlorines. Ethylene diamine is a polydenate. So it is bis. Ethylene diamine. And then we say the cobalt. Since this is the cation, the complex is first. We don't eat anything, so it's just cobalt. We put the oxidation number of the cobalt, and then we put the chloride at the end. And again, now it's a chloride because it's just there. It's still meandering all by itself. It's not caught up in this complex. I'm saying, oh, I'm caught up in a complex. All right. Was that complex enough for you? All right. Are you coordinated enough to do this? There's some really cool demos. I wish I had more time. You can imagine them. These things are beautiful colors and they can change from one to the next. And probably I'll make that as, maybe I'll make that as the picture. The picture for the KSP, the thumbnail for the KSP, that actually showed several complex ions. So they keep making these complex ions that are beautiful. All right. Do we want to do another one? No. The complexes can come out neutral. They can come out as a cation. They can come out as an anion. Again, if they're a cation, we're going to put something out here. If they're if the complex is an anion, we're going to have a cation to make it overall neutral, and then the complex gets that 8 ending. All right, let's do some shapes. Rainbow squid is here. Rainbow colors, complex ions. Because when you get to it, it has to do with vibrations. All right. And I think they may have originally been called complex ions, and as they realized, some of them actually ended up neutral overall. You might run into one on the homework. That's why they changed the name to coordination compounds. All right, shapes. You guys know these, and I just erased all my stuff, but the ones that had a coordination number, it is always your coordination number tells you the shape. So a coordination number of 3, 4, 5, 6. 6 is an octahedral. Right? So it's a square. Our complex, our ions in the center, and something above and something below. And no matter how you draw, it's called an octahedral because there are 8 faces, 4 above and 4 below. This is one of the sacred geometries, going back to like Plato or one of these guys, or Euclid. They're beautiful. They show up as crystals in a lot of places. All right, 5 is a trigonal bipyramid. These are not as common, but you could run into it. And so this was the triangle, something above, something below. It's a good review of Lewis structures. All right, 4. This is where it's funky. It depends. It could be, oh, there's pictures there for you. We learned it as tetrahedral before. It is tetrahedral if you have 4 of the same ligand. So I think we had that on the previous page, did we? Yeah, on that zinc hydroxo, the 4 hydroxides would form a tetrahedral. But if they have 2 different ones, and we will see an example below this, you actually form what's called a planar square, or a square plane. It is flat. Planar just means flat. flat as a pancake. Did I ever tell you as a story that apparently somebody got a PhD studying a map of Kansas, and then they looked at a pancake under an electron microscope, and it turns out Kansas is flatter than a pancake. There are more nooks and crannies in a pancake than there are nooks and crannies on the topography of Kansas. So it is flat, like Kansas, Midwest. So it's two-dimensional. Flat is two-dimensional. It's going to give us possibilities. Tetrahedral is three-dimensional. So the planar square happens when you have two different ligands. And again, we'll do an example down below. All right. That's not going to happen on the final, so don't worry about it. And if there was three, if there was two, it'd be linear. If there were three, again, it's a planar or trigonal planar. So it's a flat triangle, planar triangle, or trigonal planar. All right. That was a brief review. These were like the Vespers. There's then molecular shapes, which we'll look at more. I'm going to do a review on Tuesday from 1 to 3. It'll be a handout. Tape it. Since most of you probably won't study until Thursday or Friday or whenever you're planning to take your final, because you're all masters of procrastination, apparently. All right, and so you're probably busy working on your presentation. So we're going to draw these examples. All right. So it tells us we have platinum. We're going to name it. And then we're going to draw it. We're going to do like all the pieces to the puzzle. Your study set's pretty simple. It's just 2 pages. But do it with a full open heart and mind so that it gives you some good review of naming. We're going to do electron orbitals in a moment. Coordination number, oxidation number, and shapes. So many things. So many pieces all come together with this stuff. All right. These are the ligands. This guy overall is neutral. So they usually don't show the brackets. There are 2 different ligands. They each are monodenates. So our coordination number is 4. Ammonia is called amine with 2 M's. And so we'd say diamine instead of ammonia when it's a ligand, and then dichloro. This is all technically one long word. If you were a Scrabble player, you would be like, break the bank here, right? But you can show spaces. That's not a big deal to me. I'm sure there's somebody who cares out there, but the merfolk, they don't care. They just are happy you get the idea. And then we'd say platinum. And then platinum gets a 2. So the chlorines have -1 charges, and the platinum then would have the +2. Oxidation number then would be +2. It's always asking you the oxidation of the metal because it's all about the metal. So to draw these, you show your metal in the middle. And then you draw your ligands around it. So this is why we can do isomers. Normally you cannot do an isomer with a tetrahedral because there's only one way to draw it. But this is a planar square. Do not draw lines. You can draw hearts or dots. Your chlorides. Can be like that. And your NH3s have to be drawn. So the nitrogen, because it's the -1, is facing the platinum. You can draw the H's then or on the other side. Or you can just write it backwards. Write the whole thing backwards if you want. It's really good practice. It's really good for your brain. And it is dots because it is attraction. Right. There's another way to draw this. Platinum. +2. We can try and draw little hearts. The chlorides catacorner to each other. was a choice that doesn't happen in a tetrahedral. So many of you want to. I think you had a premonition of where the whole term ends up at, which is that you can suddenly, when they form these beautiful coordination compounds. And then the ammonias are also at the other corners. Again, the nitrogen is your negative part. There we go. And maybe some of you know where I'm going to be going with this. One of these is polar, and one of them is nonpolar. So how I drew the first one, it is indeed polar. It is lopsided. The chlorides do pull different than the amines or the ammonias. This one over here, because it's flat, they do cancel out. This again is a square planar. It only happens in the coordination compounds. You would not be asked, they're always hydrophilic because that's the whole point of coordination compounds. They're very hydrophilic. They love water, and then when they mix with water, they form these beautiful, beautiful colors that we see and enjoy. All right, that's one. Let's do the next one, the iron. Whoops. No, I'm not erasing very well, Rainbow Squid. You're like at the end of your Rainbow Squid. All right. Fe. This one is an octahedral. We have 6 teeth. So our coordination number is 6. All of these teeth have a charge. So our oxidation number is also a +6. Unless your teacher can't read. Nope, I could read. It is an octahedral. And we can draw this one 2 different ways. Isomers is if you can draw something 2 different ways. All right, let's do it. So the iron with the +6 is in the middle each way. And then if I had an orange, we'd do the bromide. We'll do it in red. You could put the bromides so they are perfectly balanced. So in an octahedral, something is always across from something else. And I want to use the brown. The chlorides. You guys don't like when I use green, but I'm going to. It's going to drive you all crazy. But chlorine is green. You can kind of see that. Of course, the mermaids. Do mermaids make shadows? All right, this would be our nonpolar one. Nonpolar. Because everything is straight across from its beloved. And then, of course, our other possibility is that the chlorides end up next to each other. I need to give one other piece of information here I just realized. So, bear with me. Bromide. 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 So this one is polar because the chlorides pull more. They don't cancel each other out. They're not across from each other. All right. These are called cis and trans. My second one is cis. So there is a meaning to cis. And it doesn't mean next to, but it means something similar to that. You can Google it. This is trans. Trans means across. Transcontinental Railroad. Ever hear of it? Get a chance to go see the Golden Spike Museum. Go. It's really cool. It's in the middle of nowhere in Utah. It's where they connected. So trans means across from. So here, this would be trans down here in my platinum one, and this would be cis. All right. You will run into cis and trans, yeah, when you take organic chemistry. Good times. I want to show you one other possibility because it's really cool. Maybe I'll put it on your sheet. And it is, you could have, let me just put the center here as our positive. You could have where you have a 3-3 split. If you have a 3-3 split, you could have 3 of one thing in this direction and 3 of your other ligand in the other direction. So 3 chlorides and 3 bromides, something else fictitious. You could also do where do it like that. This is the only other way you could draw it. So I have to think about this for a second. This is called FAS because they are all on the same face of the octahedral. You can really ponder this in your meditation. And this is MER. They are on the same plane. Meaning all my reds are on the same plane. Here they're on the same face, the same triangle and octahedral. The mistake students will make is they'll say, but Dr. Sherpa, there's another possibility. You should ran into this in 222. And some of you see it. I'm blessed with seeing in 3 dimensions. And some of you should all be able to see in 3 dimensions. This is the same thing as that. The easy way to think about it, the red is always across from a blue. Anyway, they are both polar because there's no way to make the 3's cancel out in an octahedral. But that's another possibility that you run into, which is FAS and MER. And if you're finding this fascinating, with MER, because the mermaid, that's kind of why I probably had to do this, is you can read about it in your book. Yeah, we'll leave it at that. All right, my mermaid outfit is telling me we gotta go, we gotta move on. I only got 1 more page. 2 more pages. All right. So we are going to do, I dropped the pin that was holding my mermaid up. Let's just wrap it around my waist. Oh, Squid. I sure hope I'm recording. Yeah. All right, we're going to do electron orbitals. Review for the final. Review for life. It's all about the quantum leaps. Really cool stuff. It's not covalent. These guys have this color. It's all about magnetism, period. Not just these, but everything is about magnetism. And we're about to move into the magnetic age, which is awesome. It's why we're here now. It's what we're going to do. And it's when all this pollution issues go away. Isn't that awesome? All right. We don't have to deal with all these other problems. Energy becomes free, right? So everything's about magnetism. Everything about atoms, everything about vibrations. It's all about magnetic attraction. Instead of forcing things apart and always forcing everything, which is what we're all like, I don't know why we do that. If you just let go of the force and instead recognize your heart is your strongest magnetic center and allow yourself to accept that, you attract. All right. So, people watching the video still, we're ready for that message. People who don't watch my videos, blessings to you. You're going to be part of the magnetic age too. All right. So the crystal field model, by the way, it says there, electron orbital theory, blah, 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 blah. It's not on the final. And, right, it is one theory. I'm not going to go into it because I don't really know anything about it. It's a pretty cool theory. But the crystal field model is, right, this idea of repulsion, blah, 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 blah. Oh, and then we get to electrostatic attraction. It's all about the attraction of the positive and negative. And, all right, so basically we're going to deal with d orbitals. Remember d orbitals? Let's just cut to the chase. There's a lot of words on my page. This room's getting really warm. I forgot to look at the cats. See if I kept it under an hour. Under 6 minutes. That's great. D orbitals, there's 5 of them, right? And we used to draw them 1, 2, 3, 4, 5. I don't know how you guys were taught these. That's why I taught them. What happens though is these 5 orbitals, it turns out, even though they're all the same, in this situation, they are not. And so there's 2 possibilities. You can draw them as 3 and 2, and there's a split. They can also be drawn as 2 and 3. So the first one is if it's an octahedral. Remember that whole thing? If you have 6 ligands, it turns out you have a 3-2 split. If you have 4 ligands and you're in a tetrahedral, it's a 2-3 split. I have no freaking idea what happens when you have 5 ligands. My guess would be it stays as 5. I also don't know what happens with planar square. It wasn't in the book. And again, if you want to really know, go ask Dr. Russell. He would love to tell you. But he's on vacation right now. All right. So there's also, we're going to do examples. You fill these in just like we did before. So there's the Pauli rules and the Hund rules, which when we put electrons in, you put 1 in each orbital. Let's just pretend for right now. So those are electrons spinning some way around their axes. So you can spin in around their axes. And then they start combining. There is something that's interesting. There is what is called a low spin. So a low spin means they're spinning really slow. And remember, these are magnetic moments. So we don't understand the difference between low and high and how fast this is going. But a low spin means basically they don't have enough spin. They don't have enough magnetic potential to make that jump until they're forced to. So they fill in these first before they go up there. All right. Doesn't matter if it's octahedral or tetrahedral. It's just a 3-2 versus a 2-3 split. It's not going to split like this on the final. This gets like to chemistry 224. But it's still good review. And it's really cool seeing. High spin means the magnetic potential of the electron is high enough that it can make the jump. And it would fill in like that. And then it would go back and start pairing up. Remember all that pairing and stuff? All right, so this one would have unpaired electrons. This one's all paired up. Oh, anybody remember the word? I can make that the last time you get to send me an email. This first one is diamagnetic because everything pairs up. There's no unpaired. And this one is paramagnetic. Most things are paramagnetic. This one's extremely paramagnetic. All right, because there's unpaired, it means there's a magnetic something or other going on. Blah, 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 blah. I have a lot of words here. Wow, I apparently read the book at one time. But this whole thing of if it has a high spin or low spin and how the split happens explains the colors that we see. And I don't know how they figured that out, but it's when we see magenta, red, deep blue and stuff, has to do with these, or the colors of our beautiful mermaid. Yeah, and what they complex with. So chromium, when it complexes with hydroxide, is green. When it complexes with aqua, water, it's a blue-violet to orange. Sometimes it's orange. What's blue-violet to orange? That's quite a difference, except they're across from each other, I think, on the beautiful wheel. No, they're not. And then chromium with the NH3 makes a beautiful magenta. All right. Anyway, we're going to do an example of each one, and then we'll do a practice. Maybe. All right. We'll do the tetrahedral one first, because I have that on my page. And I don't have anybody here to politely tell me if you can see the red. I can see the red in the video. Let's name it. Let's go through a whole shebang. All right. We say the potassium first, because it is the cation. Cats come first. If you want, you can show your picture of your cat. Your cat can be meditating very peacefully. All right. You should always draw your cat's tail. And I can draw his paws. 4 chlorides. So 4 is tetra. There is a space here. Tetrachloro. These are my 4 ligands. This is my coordination number. And then we say the cobalt. It would all be one word, but I'm going to write underneath cobalt. Oh, this is my anion. So I have to say the cobalt 8 something. And I have to give a number to it. And it would be a 2. It's back to that question you asked, Alexander. When in doubt, go with 2. The chlorides all have a -1, which would be -4. The potassium has a +1, which would be +2. So the cobalt's oxidation number is 2. All right, where this becomes important, periodic table. If we normally did cobalt, just remember the shortcut, you say cobalt is there, number 27. So we're going to start with argon, number 18. Doing electron configurations here. Oh, by the way, coordination number 4, they're all the same. This would form a tetrahedral. That's important, the shape. We cannot do any isomers because all 4 of the ligands are the same. That's why we're doing a tetrahedral. All right, so cobalt. Normally, after argon, you come into the 4th row, and you're in the S block. So you guys remember the first 2 rows in the periodic table? You have S, then you have D, and then over here you have P, right? And then down below you have the Fs, and the S's and the P's go with what row you're in. So potassium and calcium are the 4 S's, and then from scandium over to zinc, but we're going to stop at cobalt, we would have 3D7. That would be how we normally would do it, and we draw our stuff. But this is not normal. This is complex and cool and beautiful and fascinating. The cobalt has a +2. It loses the outermost. The S's are gone. This is why, Alexander, your question about the 2, this is why 2 is the most common charge of the transition metals. They all go to a 2. It's usually, I think, for every single one, a 2 is a possibility. And is the most common possibility. And it's because they lose their S's. So we are left, since it only lost 2, with 3D7. And then we have to be told, and it does tell us, this is a low spin opportunity. So we're going to put 1, 2, 3, 4, 5, 6. You know what? This was not a good question. We should have done a different question. 3D7. Let's pretend like it had a +3. This would have been the one that wasn't there in a low spin. If it was a high spin, we would have filled 5 and then started. All right. That was like easy, because if you did it right or you did it wrong, you would have gotten the same answer, because low and high spin would have came out the same. That should be a bonus, like, email. I don't even remember what the other one was. I've lost track of all of this. But randomly, a person will send me one and remind me. And then I'm thrilled, because somebody actually listened this long. All right, we're going to do one more. We named that. I need to do a high spin. Draw, high spin. Oh, that would have been a better one. All right. I'm going to erase. So you guys know what the question is because it will already be on your page. And we are going to do, let's do an F. Iron's awesome. Ethylenediamine. Oh, we should have done one with gold, huh? Put an H2O. Put 2 chlorines. Put another chlorine on the outside. Alright. So, let's go ahead and go through naming. I'm going to switch to black. My crown's giving me a headache. Alright. So, we name the ligands first. Alphabetical order. Water is aqua. It's no longer W. It moved to the front of the alphabet. So we say diaqua, dichloro, and then the EN is ethylene, diamine. Let's do our little mermaid shuffle. Ethylene, diamine, and then we say the iron. I'll say iron again. The iron doesn't eat anything. It is going to be a coordination number of 3 because of the 3 chlorides. And then we put a chloride at the end. And if you'd rather, instead of saying iron, if you'd rather say ferric. Beautiful. All right. Coordination number is 6. Ethylenediamine counts twice. That's important because it's an octahedral. So what that means is we get a 3-2 split. And the iron is a +3. So let's do our electron configuration. So normally iron, we would say argon, 4s2, 3d6. It's a +3, so those 2 are gone, and 1 more. So it's a 3d5. We're going to do this as a low spin. The previous one did not matter if it was low or high, so I guess I can change it to a high spin on your notes. You guys won't know. We're going to do this one as a low spin. If it was high spin, you get 1, 2, 3, 4, 5. Let's do it both ways. Let's do a low spin. And then let's do a high spin. So high spin, still the same. So one of the ways they explain it is they say the gap is smaller. It's somebody's idea. Your teacher's idea has to do with the electrons. Always has to do with the electrons. Its magnetic potential is not high enough here. It's a low potential, so it doesn't make the jump because it didn't want to, because it gives a different color. All right, here we would have 5, and if it was high spin, it would end up like that, and we'd get a different color. High spin feels the same way as if you had 5 straight across, how you learned in Chem 221. Low spin, you get different and you get different colors. We're going to also draw this one out. This will be our last piece of excitement here. Just because I love drawing. All right. So, what should we draw? We can draw over in the lower corner. Let's draw up here. So we have the Fe is a +2. We can go to the chlorides. Now, this is the piece you have to be careful about. The ethylenediamine is a double tooth. So you only draw one ethylenediamine. It will come out like that. No matter how we draw this, it's going to come out polar. And when you draw the water molecules, you have to draw them out. And it is the oxygen that is attracted because of the negativity. So the oxygen is attracted to the positivity of the chloride. 6 teeth. That's an octahedral. This has a positive, this had a positive 3. So there would still be another chloride, but it didn't make a tooth to it. So we didn't have 7 teeth. And that's it. That's all I got. So, many blessings, and I will see you all soon. Ta-ta.